In the late 18th century, the physical sciences faced a mathematical ceiling. Astronomers needed to predict celestial mechanics, but their models were crippled by sparse data and high observational error. On January 1, 1801, Italian astronomer Giuseppe Piazzi discovered the dwarf planet Ceres, but he could only track it for 40 days before it disappeared into the sun's glare. The existing nonlinear equations of planetary motion demanded vast amounts of observational data to formulate an accurate prediction. Without it, the celestial body was lost. A 24-year-old mathematician named Carl Friedrich Gauss solved this problem. He successfully predicted exactly where Ceres would reappear by applying a nascent technique, maximum likelihood estimation, to extract the true orbit from the surrounding observational noise. Gauss built his method on a strict epistemological assumption. Observational errors naturally cluster symmetrically around the truth, and massive deviations from that center are exponentially improbable. Visualizing these scattered, flawed measurements, Gauss defined the error algebraically as delta equals x minus the mean. Setting the derivative of the log likelihood function to 0 mathematically collapses this noise into a single arithmetic mean. Integrating this relationship derives the standard normal probability density function. This derivation took uncertainty from an unavoidable physical nuisance and structured it into a governed, solvable mathematical architecture. Over the subsequent century, Gauss's theoretical work evolved from classical celestial mechanics into the formalization of modern statistical estimators. The culmination of this evolution was the Gauss-Markov theorem, which serves as the baseline for statistical truth in data science today. This scatter plot compares different estimator lines. The theorem proves ordinary least squares, or OLS, guarantees the lowest sampling variance among linear unbiased estimators. Isolating the residuals exposes the minimal conditions. Errors only need to be uncorrelated, possess zero mean, and have finite variance. Crucially, these underlying errors do not strictly need to be normally distributed or independent for OLS to provide the lowest variance. However, this classical theorem carries a severe engineering limitation. It is strictly restricted to linear estimators. While OLS remains the baseline of classical inference, modern machine learning demands nonlinear frameworks to process complex, high-dimensional datasets. Modern data science requires scaling Gaussian logic far beyond its classical limits. Instead of estimating a distribution over scalar parameters, data scientists now infer complete probability distributions over entire functions. This execution model is the Gaussian process. It acts as the infinite-dimensional extension of the multivariate Gaussian distribution. Deep neural networks rely on emergent, opaque representations. Gaussian processes offer an explicit alternative. They are nonparametric and provide exact, mathematically interpretable bounds of uncertainty. This 2D bell curve extruding into a 3D manifold defines the covariance function, or kernel, which dictates the strict geometry of the probability space. The mathematical tether linking two proximate points shows how the kernel forces inputs with similar features to output highly correlated results. Engineers deploy this architecture in Bayesian optimization pipelines, using it to autonomously navigate and tune the complex hyperparameters of deep neural networks. The interaction follows a strict updating loop. The system samples an unknown, expensive black box function, updates its beliefs via Bayes' theorem, and calculates both a predicted mean and a quantified variance. An acquisition function then processes these outputs. It continuously weighs the algorithmic trade-off between exploitation, sampling areas where the predicted mean is optimal, and exploration, sampling regions where the variance and uncertainty are highest. Gaussian processes provide the mathematical certainty that black box networks lack, serving as the primary framework for navigating unknown, expensive parameters. However, executing these Gaussian systems at scale triggers massive infrastructure and memory constraints. The primary technical bottleneck of standard Gaussian processes is known in data science as the big N problem. To make a single prediction, a Gaussian process must calculate the inverse of the covariance matrix across all training data points. Plotting this computational cost, the time complexity scales cubically, while memory storage scales quadratically as the dataset grows. For modern datasets containing millions of observations, running a naive Gaussian process is entirely intractable. The hardware simply cannot execute the required matrix inversions. Engineers bypassed this physical limit by proving a profound mathematical workaround. As the width of a neural network's hidden layers approaches infinity, the network converges in distribution to a neural network Gaussian process. By recursively applying deterministic functional mappings through layers, data scientists can compute exact analytical kernels. This allows them to evaluate network architectures analytically without ever running stochastic gradient descent. This convergence identifies Gaussian mathematics as the analytical limit of neural network architecture itself. In the highly visual realm of modern spatial computing, Gaussian logic is currently displacing neural networks entirely. Beginning in late 2023, 3D Gaussian splatting rapidly overtook Neural Radiance Fields, or NeRFs, as the state-of-the-art technique for neural rendering. NeRFs operate on an implicit paradigm. They utilize massive multi-layer perceptrons to memorize and calculate the lighting and geometry of a scene. The left side of this split screen shows the latency bottleneck of NeRFs. The system must fire a ray and run a massive neural network for every single pixel it attempts to render. The right side demonstrates 3D Gaussian splatting. It uses an explicit paradigm, defining the space as an array of discrete, mathematically editable 3D Gaussian blobs. Each individual Gaussians is mathematically anchored with explicit properties: a 3D position, a covariance matrix defining its ellipsoidal shape, an opacity value, and spherical harmonics to calculate view-dependent lighting reflections. To render an image, the system mathematically projects, or splats, these 3D Gaussians directly onto a 2D camera plane using highly parallelized GPU rasterization. This architecture forces a strict engineering trade-off. 3D Gaussian splatting bypasses the neural network to achieve real-time speeds of over 100 frames per second, but the explicit storage of millions of individual Gaussians demands up to 1.5 gigabytes of VRAM. Recent optimization frameworks like MobileGS address this by using depth-aware, order-independent rendering. This eliminates the massive depth sorting overhead required for alpha-blended transparency, allowing the system to run on constrained mobile devices. By deliberately stripping deep neural networks out of the inference pipeline, 3D Gaussian splatting proved that explicit mathematical structure can beat emergent, learned parameters in raw rendering speed. Gaussian systems excel at spatial coherence and exact uncertainty mapping, but as these models expanded out of astronomy and into complex human industry, they exposed their most catastrophic failure mode. Recall Gauss's foundational assumption from 1801. Gaussian models are built on the strict assumption of thin tails. They dictate that extreme deviations from the arithmetic mean are exponentially improbable. This assumption breaks down disastrously when applied to heavy-tailed, nonlinear human systems, particularly in global finance and psychology. This specific limitation materialized as the black swan problem during the 2008 global financial crisis. This chart illustrates a standard Gaussian bell curve superimposed directly over a heavy-tailed Cauchy distribution. Wall Street quantitative analysts used Gaussian Copulas to model financial markets, miscalculating risk by treating the market like a clean bell curve. Zooming out aggressively on the x-axis, we plot a 25 sigma data point. Under the Gaussian level, simultaneous asset collapses were labeled 25 sigma events. They barely exist on the standard curve, yet they fit perfectly within the fat tail of the Cauchy distribution. Under a true mathematical normal distribution, a 25 sigma event is so rare it should not occur within the lifespan of the entire universe. Because the models ignored non-Gaussian kurtosis, they treated the impossible as fact. Gaussian logic remains the optimal mathematical mechanism to extract signal from natural noise, but if engineers mistake chaotic human behavior for a perfectly symmetrical bell curve, the architecture guarantees systemic ruin.